All right, I guess we can start. So, concurrent garbage collectors. So my name is Simone. I work for the company behind the Jetty project. But today I'm not talking to you about Jetty, but I will be talking about garbage collectors because they are a passion of mine. And so I've studied them, and we actually need to know them in order to suggest to our clients that use Jetty which one is best for them. So let's dive into this. So this is the status of the garbage collections that are present in Hotspot. The first and probably the oldest one is called the parallel collector. It works on 2 generations, and as you can see from the red bars, it uses stop-the-world algorithms to collect garbage. Stop the world means that the application threads are completely stopped by the garbage collector. Then the garbage collector threads run, they clean the heap from the garbage, and then they restart the application threads. What's the problem with this algorithm is that when the garbage collector runs, the application is completely stopped. And if the garbage collector has to do a lot of work, then it means that the application stays frozen for a lot of time. And so this is not good. So in order to cope with this problem, another collector has been introduced. It's called the Concurrent Mark and Sweep collector. And it works in this way. The young generation is still collecting using a stop-the-world algorithm, but the old generation is now collected concurrently with the application. This means that there are typically, and this is true for almost all the concurrent collectors, there are very short stop-the-world pauses at the very beginning of the collection, but then the garbage collector figures out an initial set of information which is enough for the collector to then continue to run concurrently with the application. So the garbage collector stops all application threads, collects the minimal information that it needs, then restarts the application threads, and also runs concurrently with the application. And while the application is actually serving requests or doing database queries and etc., the garbage collector also runs and collects all the garbage. CMS works in this way. The problem of this particular collector is that it does not compact the objects in the old generation. So it is able to perform a concurrent collection of garbage, but if it runs for a lot of time, it happens that the old generation gets filled by objects, and then these objects eventually maybe die, so there's a little spot of empty that has been collected by the collector, and eventually over time, the old generation becomes like a Swiss cheese. And it's completely full of little holes, but there's not a hole that could be big enough if I want to do, for example, a big allocation. So maybe if I sum all the space of the holes, I do have the space, but I do not have that space in a contiguous portion of memory. So this problem is known as the fragmentation problem. And so we need another collector to solve this, this problem. And so here comes G1. G1 is the default collector since JDK9. And the way it works is that, again, the young generation is using a stop-the-world algorithm. The old generation is collected in 2 phases. There's a concurrent mark that marks all the objects that are actually alive. And then the collection and the compaction of the old generation happens in slices, basically. So the garbage collector knows which objects is alive, and therefore it can say, okay, I have to do this whole amount of work. I split the work, for example, in 8 pieces, and then I'm going to do 1 piece first, which is probably the one that covers most space, okay? And then the next collection, I do the second slice. And then the next collection, I do the third slice, and so forth. So this it is in between CMS, because it solves the problem of CMS, because by collecting the old generation and compacting it, I solved the fragmentation problem the CMS had. But it is different from the parallel collector because rather than doing the whole generation in one single step and therefore stopping for a long time, it does the whole generation in pieces. And so each piece, of course, stops for a shorter time. But it's still a stop the word pause, which not really good. So finally, it took a while, but eventually now we have the luxury of having two new collectors that are working, as you can see, on a single generation only. There's no multiple generation, just one generation. But these collectors are both concurrent with the application and can do also concurrent compaction, which is the thing that was actually missing from this point. Not only the marking that was done by G1 and CMS, but also compaction that was missing from all the other collectors, especially because there are single generation for these collectors. Even what before was in the young generation that was always collected by the previous collector using a stop the word algorithm, in these new collectors, the young generation doesn't exist anymore. There's only one generation, but that generation is collected concurrently. So there's no red bars anymore, just green bars, and everything works really, really well. So what's the problem with these collectors, though? Well, the problem is exactly in their name. They are concurrent with the application, and by the definition of that, they run into a race with the application itself. So, for example, if the garbage collector says, I want to move this object from here to there, and exactly at that moment the application accesses that object, it's a problem. And so this is the problem. We call what is called the from space, the place where the object initially lives. Okay, so there's an object pointing to our object that exists in there. Then the garbage collector comes in and says, okay, I want to move this object to a different place, to compact the heap, for example. All right, so it makes a copy of the object. Then the application comes in and says, oh, but I want to change a field now. And so writes a equal 3 here, and but where? Of course, the new object that has been copied by the garbage collector is not known to the application, doesn't know that there is a copy of the object over there. And so it changes, follows the pointer and goes to the place where the object was. But then the garbage collector continues and says, oh, well, okay, since I moved this object, then now I just update the reference from the other object that was pointing to this one that I just moved, and by updating the pointer, I've now lost a write, okay? And so this is a big problem, and we will go into details about how these two new collectors solve this problem. So basically, we will understand how they work, how they can possibly work, and why they're so much better than the previous collectors. So how do these collectors solve this concurrency problem? They employ two tricks. The first trick is to store metadata information about the object or the reference to the object. And the second thing is that they ask to the just-in-time compiler to help them. And so what the JIT does for garbage collector is to inject a little bit of code every time we load or write a field reference. And so by injecting this additional little bit of code, that is garbage collector code eventually, the garbage collector is able to run a little bit of code that helps the garbage collector itself to figure out these races. We will go into details about this. So there are two kinds of code that the JIT injects to help the garbage collector. One is done when you load information, and so that's called typically a load GC barrier. But the term barrier simply means a little bit of code that gets executed by the runtime. And then, of course, there is the correspondent of that on the writes, and so that's called the store GC barrier. So by using these two tricks, we will see that ZGC and Shenandoah will have different tricks on how to use these, different but similar in a way, and they will be able to create an algorithm that is safe and doesn't crash your Java virtual machine, doesn't lose writes, and so forth. All right, so let's dive into ZGC. ZGC is present since JDK 11. So who's still on JDK 8 or less than 11 here? Not so many, like half of you, which is fine. So ZGC is available in OpenJDK 11, so it is available in Adopt OpenJDK builds and also in the Oracle OpenJDK builds. It's, as I said, the concurrent compaction, single generation garbage collector. The big limitation for ZGC is that it is only available as of this time for Linux 64 bits. This means that it will not use compressed pointers, which means that you have small heaps. It will still use 64-bit rather than 32, even if you have small heaps. There's an ARM port which is underway, but basically that's the only platform that you will be able to use ZGC on for now. It is based on regions. So it divides the heap into regions that in ZGC they're called Z pages. There are 3 kinds of them, but you can imagine that basically the single generation that ZGC allocates is divided into these regions. And the way that ZGC compacts the heap is basically this. It allocates in one region, then eventually the object allocated in that one region some of them will be dead. And so what ZGC does is basically takes the alive object in one region and moves them to another region. And then the whole region that before was full of objects, most of them dead and only few alive, can now be completely recycled. And the new region would only contain the few objects that are still alive. In this way, it is compacting the heap. Okay. The trick that ZGC uses to store metadata about this object is to use what they're called colored pointers. What does that mean? If you know, even if a pointer is 64 bits, modern CPUs cannot use more than 48 bits to actually address memory. Okay? That means that there's a lot of bits in a pointer that are not used at all. And so ZGC exploits that and it says, okay, I'm going to use 44 bits, which goes up to 16 terabyte of addressable memory for the address of the pointer. But then I'm going to use 4 bits as metadata information that I'm going to use in order to figure out whether the object that this pointer points to is a good object that I can, for example, move around, collect, or if I have to do some additional action on this object. And the other bits are just basically unused. But what happens when you change a bit of a pointer? Well, this happens, that you have virtual memory, but then if the address looks in this way, like 001, these are the colored pointers, and then the address of the pointer, then you are in a region of the virtual memory. But if you change one of those bits and you make it become 010 and then the address, you are in a totally different region of the virtual memory, and so forth. If you go 100, you are in yet another region. Okay, so ZGC uses this trick on Linux. It basically does this. It multi-maps into virtual memory the same physical memory. And so by doing this, it is free to change the value of those colored bits any way it likes, because no matter what is the value of the colored bits, it doesn't matter, because from the virtual memory, they eventually end up in exactly the same place in the physical memory, okay? So even if I would move this, immediately teletransport to a totally different address, still this is a virtual address that points to a real address in physical memory, and therefore I will not, I will point to the same object all the times. This has a side effect, though, that if you look at tools that right now report how much memory is my process using, these tools may report that the process is using 3 times more memory than actually the process is using. This is because the resident set size here, the RSS, it is a tool that doesn't take into account, for example, that the virtual memories or parts of the virtual memory, they're pointing to the same physical memory. So if there are mappings that point to the same region of memory, RSS counts them as different ones. And so it reports a 3-size memory. Is this a problem? Well, it could be, because if you go to the cloud, for example, there are cloud services that are present almost all the times that are called, for example, in AWS, they're called out-of-memory killers. That they say, well, okay, if you started this process, but this process is using too much memory, then I'm going to kill this guy because something is wrong. And so, for example, if you start ZGC with a heap of 16 gigabytes, it is, RSS reports almost 50 gigabytes. And of course, if you have like a 32 maybe gigabyte machine in the cloud, then if RSS reports 50, then the out-of-memory killer jumps in and says, oh, we are at 50, you only have 32, I'm going to kill this process, okay? And so that's not good. You want to use maybe not the default out-of-memory killers, maybe something else, for example, as MEM reports. This is a PSS, it's a proportional set size. It's a different metric that actually reports correct memory usage when ZGC is used. So the second trick that ZGC uses is what I said before. It is help from the JIT to help the garbage collector. In particular, ZGC only uses what is called a load GC barrier. And it works in this way. So here we have some Java code that loads a field, okay? So you see it's a load. I have an object, I want to reference a field, and I need to load the field, all right? And so here comes the load barrier. The JIT looks at the bytecode, sees this pattern, you are loading a field, therefore I'm going to inject a little bit of code here, all right? How does the code look like, the machine code look like? So don't panic, it's assembly, but I'll explain how it works. So RDE is the registry that contains OBJ, okay? This notation means just take the address of OBJ and move 16 bytes, 0x10, 16 bytes forward. What's there? Well, there's the field, all right? So 16 bytes past an object, there's the field, the reference. And so load this field reference into the RSI registry. Then you go to the R15 registry, which is a registry that is being filled by the runtime with garbage collector information. And so again, you take this data structure, GC data structure, you go 32 bits forward that, you load what's there, and then you compare that information with the pointer to the field, okay? So what's this, basically? This information here, the GC data structure, holds the right color in that particular moment, okay? And I want to test the right color with the current color of the pointer. If the color is good, then I do not have to do anything. We are in the right phase. I'm not moving object around. I'm not doing special things. You can just, use this field. But if the color is wrong, then you're going to take what is called the slow path, okay? So the color of the pointer is now wrong. I need to do some action. The action that I need to take must be atomic, because remember, we need to always do atomic operation, because otherwise the application is running concurrently with us. And so there must be, at a certain point, an atomic operation that either is won by the garbage collector or is won by the application. And the action that I need to take depends on the garbage collection phase. We will go into details about with an example about this. So as I mentioned, the action depends on the garbage collector phase. What are the phases for ZGC? Well, there's an initial, you see the red bar here, stop the work phase, where the garbage collector collects all what they're called the garbage collection routes. Okay, so the object graph routes. What is a route in Java from the point of view of a garbage collector? For example, local variables that you're actually using in your threads. Okay, so if you're using a local variable, that's a route. It's a live object that you're actually using right now, and everything that this object points to is alive because I want to be able to, navigate the object graph and do things with this guy. And so there's a first initial phase where all the routes are collected, and then concurrent mark can start. Concurrent marking basically just go through the object graph and collects and says, okay, this object is alive, this object is alive. Not only that, but also collects liveness information. For example, imagine there's a page, a Z page, that has been allocated. So many objects have been put into that page. But then the garbage collector runs the marking and never, ever goes into that page. What does that mean? It means that all the objects that are in that page are garbage, right? So if the garbage collector knows, well, I never even went visiting that page during the marking, it means that the garbage collector immediately knows that that page can be immediately recycled because everything is garbage in there, all right? Then there's a phase, another stop the work phase called mark end, where ZGC stops, eventually does some internal flip of state that needs to be atomic, and then prepares for the next phase, which is again a concurrent phase. As you can see, the garbage collector threads are running concurrently with the application threads. This phase is the one that goes and does, for example, reference processing, which is soft reference, weak reference, phantom reference processing, unloads classes, frees memory pages, prepare for the next phase, which is relocation, and says, okay, I've marked all the object graph. What are the pages that contain most garbage? Because those are the ones that I want to go through first, because I will recover so much space doing very little work, right? Imagine one page containing just one live object. I just copy the live object, and then the whole page is recyclable, okay? So I've done very little work for a lot of space regained. Again, there's another short stop the work phase here called the relocate start, and then there's concurrent relocation. So relocate start, I decide what are the pages that I want to compact, and then once I decide that, just concurrently, I'm just moving all the object around with the application still running, okay? Eventually, because I have moved all the object into a different page, the other objects that are pointing to the one that I moved still point to the old place, right? And so the last phase of the garbage collector is to basically navigate again through the object graph and repointing, rephasing all the pointers, writing all the pointers to the new places where the new objects have been copied, okay? So that the object graph is now, again, sane, is not pointing to places that were there before, okay? This is called remapping phase. And because the remapping phase has to navigate the object graph again, what was the other phase where I was navigating the object graph? It was marking, right? So actually, what happens is that the remap phase can be delayed until the next garbage collection starts, and then I'll just do the remap phase of the previous cycle at the same time of the marking of the next cycle, okay? So let's look at an example. In particular, the relocation is how does ZGC solve the problem of I am relocating an object, but an application is actually, looking at this object, maybe writing a field to this object, etc. So the garbage collector starts, takes this one on the far left is a root, and collects the route and then navigates the object graph. So it says, okay, the route doesn't need to be relocated. Let's leave it there. But then it follows the pointer and says, okay, this object needs to be relocated. So it creates a copy, and then, as you can see, the pointer is not changed, but it creates a copy, and the copy points to the previous places where the children were. And then navigates these pointers and says, okay, I'm going to copy this object and this other object, okay? Where does it store information about these copies? It puts aside a concurrent map, let's say for simplicity, where it stores the previous location, previous address, and pointing to the new address. So, for example, if this object is B, it's going to be pointing to B1, okay? It's a concurrent map, C to C1, D to D1, right? Then the garbage collector says, okay, this subgraph is finished. I want to go up and do the other part of the graph, right? But before it does that, the application comes in and says, oh, but I want to access this object now. But because the garbage collector is now running and it is doing things, there's a load barrier. So the application sees the load barrier and it says, oh, is the color of this pointer the right color? Look, the color of this pointer is, the pointer hasn't been touched yet, so let's say it has one color, but the garbage collector has, as a main color, a different one. And so the colors of the pointer and of the state of the garbage collector do not match. Therefore, I need to take the slow path. What is the slow path? Oh, what phase am I in? I am relocating objects. Okay, so I need to relocate the object. And so the application actually does the work of the garbage collector. The application thread is relocating this object, okay? And so it creates a copy and stores the metadata information in the concurrent map, all right? But exactly at the same moment, the garbage collector arrives and says, oh, this pointer is not of the right color. I need to make a copy. And so it creates a copy of, made by the garbage collector. And then what? And then it tries to put into the concurrent map the same information and say, here's where it was before, here's the new place that I would like it to be. But when it goes into the concurrent map, it finds that the entry is already there. And so the garbage collector says, oh, I lost this race, okay? Okay, I lost this race, what am I gonna do? I'm gonna just throw out my copy, it's done, and I'm taking the information from the concurrent map where it is right now, the object. Okay, and it takes the E1 value that has been created by the application. Then the garbage collector, well, then the application was about to use that object. For example, it was calculating the hash code or whatever. And, now the garbage collector has to navigate and finish to navigate the object graph. So the garbage collector goes on, throws away his copy, but then follows the pointer and finishes to navigate the graph for its children. And so it creates another copy for the last children. And so F pointing to F1 at this point is made by the garbage collector. And, at this moment, the complete graph has been navigated. And of course, what's the next step? Well, the next step is this one. It is to adjust all the pointers to the new places where the new objects are, okay? And so all the really dark gray objects can now be, they are in some page. All the new ones will be in a different page, and so the old page can be just thrown away, and, the algorithm has worked. So this is what the algorithm for ZGC works. As I said, this is how I studied ZGC. I looked at the code. I've made my experience. I've run a few benchmarks with it, with especially benchmarking Jetty as it was working on ZGC. But the main guys, which also I owe much of my presentation, are the actual guys that are working, implementing ZGC. So Per Liden, Erik Österlund, and you can find their presentations online on YouTube. They went to other conferences and gave detailed presentation about ZGC. There's a project wiki and there's a mailing list that you can subscribe to. They are very, very responsive in the mailing list. If you have a problem, a doubt, or you want to report, I'm using ZGC, I got a crash, here's the crash dump, that will help you out. They are super cool in this sense. So it's a very interesting project. Questions about ZGC before we move on to Shenandoah? Something that is completely unclear, right? All right, let's move on and let's look at Shenandoah. Shenandoah is a project from Red Hat rather than Oracle. It is been the source code of Shenandoah has been merged into the source code repository since OpenJDK 12. However, you can find the binary build of Shenandoah will be available in Adopt OpenJDK, but not available in the Oracle builds, okay? Because Oracle doesn't want to build something that is not Oracle into their own binary builds and then having people that says, hey, I'm trying Shenandoah, I have this problem, and then send this email to Oracle. And Oracle says, yeah, I don't know, you can, you know, they don't want this kind of emails, so it's fine. I mean, that's totally understandable. What is the big difference between Shenandoah and ZGC? That Shenandoah is actually available for any architecture, and Red Hat has done an outstanding job at backporting Shenandoah from the current JDK version, which is today is 14, but it's present in 13. 12, of course, is already dead, so nobody looks at 12, but you know, they have backported it to 11 and to JDK 8 as well. So for those of you that are still on JDK 8, you can use Shenandoah. And because Shenandoah doesn't depend on architecture, so it doesn't need a 64 pointer to work for colored pointers or algorithm like that, it can be used with compressed pointers. It can be used on very small heap. It can be used in 32-bit architectures, and it's, you know, basically you get all the benefits. It is available, Shenandoah, on many platforms. It is a garbage collector that has been derived from G1. And so from G1, it inherits the fact that it's being divided, the heap is divided in regions. It inherits from G1, for example, the marking algorithm, which is exactly the same as G1, while, for example, ZGC had a different marking algorithm because it was using different techniques. Before we go into the details of how Shenandoah works, I need to do a refresher on the object header. And so this is how an object is laid out in memory by hotspot. Okay, so this is different from every JVM brand, but for hotspot, it works in this way. There's a word which means 32 bits on 32 bits architectures, or 64 bits on 64 architectures, okay? So this one is a single word, and it's called the mark word. Then there's another word that is the class word. Basically, this is a pointer to the class object inside the Java virtual machine, so that I know what class is this object. Like if you want to do an instance of, you basically are comparing this thing, okay? So it's a pretty quick operation because you just go there to the object layout and say, okay, is the pointer here? Is this the same pointer as this other guy, right? So it's super fun. And then you have the fields, okay? This is the layout of an array. It only has additionally the array length at the beginning, but then you have all the slots, but you know, it's okay. What's in the mark word? Well, the mark word historically has been used to store anything else that was useful somehow. For example, did you know that if you call system identity hashcode, the hashcode that gets generated is actually stored in the mark word? So it is stored there. If you lock objects or stuff like that, there are lock bits, especially for biased locking, that are set in this mark word. And by the name, it is also used by certain garbage collectors to mark, flip a bit and saying, well, I've already visited this object, I want to mark it, and I want to say, well, you know, if you have cycles, for example, in the object graph, you don't need to visit the object again, because you will go here, find that the mark bit is flipped, and therefore you say, oh, I already visited this object, I'm good, all right? So Shenandoah actually came in two versions. The old version is kind of still alive, especially in JDK 11 ports and JDK 8 ports. You will find this version of Shenandoah right now. In the future, of course, Shenandoah 2.0 will be backported all the way back, and therefore in the future you will have a better Shenandoah. But for now, you still have 1.0. And so here's the status of, you know, three objects pointing to each other. So you have this field pointing to the beginning of the object of another object, right? So Shenandoah, what it does is it adds a forward pointer before the actual object. And so this is the structure for Shenandoah 1.0. There's this additional pointer that points to itself, okay? Why is that useful? Well, I want to be able to maintain this invariant where I want to be able to read and both from the from space and to space copies, but I also want to be able to write to space copy. This is because I never want to write on the from space copy, because as we see at the very beginning, if we then move the pointer, we have lost the write, okay? And so the way, the trick the Shenandoah uses in this case is to employ a load barrier that contains the information of where is it the actual copy that I need to operate on, right? And so this is maintained by the forward pointer that there is at the very beginning. So every time I go and visit an object, I need to do this operation. I need to take the pointer to the object, move back 8 bytes, and then load that reference back into the R10 registry, right? And so I basically go to an object, go 8 bytes back, read the forward pointer, and which goes, you know, sends me 8 bytes forward, because typically most of the time I'm just going, you know, back and forward. I'm pointing to myself, right? Shenandoah also uses write barriers, not only load barriers like ZGC only does load barriers, but also has write barriers. The write barrier is very similar to the other one. It says, okay, let's load some GC state here, and then compare the GC state and see, for example, this operation says, is the GC state 0, right? If it is not, then take a slow path, and then you have to do things. And so let's look at the problems that Shenandoah 1.0 had. And so the fact that there is a pointer before the forward pointer consumes memory. And so that's a problem. The worst case where you do not have any field, and so you have the mark word, the class word, and then you have the forward pointer, which is another word. And so that's 50% more usage of memory, which is not good. But in general, because you have fields in your classes, you know, the overhead amounts to 5–10%. And then it had complicated barriers which were slowing down things and etc. But fast forward to Shenandoah 2.0, this is the same situation. Now Shenandoah 2.0 does a different thing. It has eliminated the forward pointer, which is now stored in the mark word here. So when Shenandoah makes a copy of an object, it just installs the forward pointer, overriding whatever was in the mark pointer. Okay, all the information that was there is now copied into the new copy. But now, what is the problem? The problem is that I have to maintain a stronger invariant because the old object is now overwritten by my metadata information, and I cannot use it as an object anymore. I could just use it for the garbage collection purposes, but that's it, right? And so the invariant is now stronger. Everything reads and write only happen in the two-space copy, all right? So the barrier is now that Shenandoah is now employing. Remember, before the barrier was read the forward pointer, but now the barrier is actually much simpler. It's like load GC information. Is the GC running right now? It is this GC information, is it 1? If it is GC is actually running, then you have to pay attention because there's something that could be wrong, right? If it's not running, we're good. These are the phases of Shenandoah, very similar to ZGC. Mark start, very short stop the word, concurrent marking, mark end, concurrent evacuation, which is relocation, was called in ZGC. Update reference, which is remapping in ZGC, exactly the same concepts that were present there. At the same, as ZGC, you can run the update reference phase concurrently, well, not concurrently, but at the same time as the next marking cycle. But Shenandoah also has one mode, which is a different one, where it does everything in just one pass. So you can have a single stop the word phase at the beginning, and then you can do mark, evacuation, and update reference all at the same time. Let's do the example that we did for ZGC and see how Shenandoah solves this problem in the same way, right? So here's an object graph. And Shenandoah runs and makes a copy of the object, okay? This is from space, goes into to space. Then the application comes in exactly at the same time. It triggers the load reference barrier, okay? So it triggers a GC barrier that has been put there. And so the application says, okay, the barrier has triggered, I need to run the slow path, what do I need to do? Oh, well, we are evacuating object, and therefore I need to create a copy of the object. So the application also creates a copy of the object, all right? But then they will do this atomic operation, which is what? They will need to install the forward pointer in here, right? And they will both compete to write that particular place of memory at the same time. And only one of them will win, all right? So in this case, the application wins. And so the copy of the garbage collector gets thrown away, and the application copy has won. If another thread from the application now comes in, what will happen? It will go from here, arrive here, it will see that there is something, the garbage collector is actually running. It will say, okay, is this object being collected at this time? Yes, it is. Okay, does it have a forward pointer? Yes, it has. Okay, so let's follow the forward pointer, go to the real copy, the actual live copy of the object, and then we'll do the reads and writes in the correct copy, all right? And so this is it, and then the remapping phase or update reference phase, as it's called in Shenandoah, will just point to the new copy. These are heuristics for Shenandoah, so modes that you can tune Shenandoah to say, for example, I want to maintain a specific free heap amount, or I want you to start garbage collection the moment you trip a threshold, or I want, for example, there's an aggressive mode where you run back-to-back garbage collection. So you start, finish one, you start immediately the other one, start, and so forth. Again, references, Alexei Shipilev and Roman Kenke are the main developer of this project. There's a wiki, there's a mailing list, reactive as the ZGC one. They're super nice. And so I really recommend, if you're interested in it, to subscribe. Questions on Shenandoah. And then I have a last slide for conclusions. I guess it was clear. Then let's go to conclusions. Okay, so the key point of this presentation is update your JDK and give this concurrent garbage collection a go, because they are awesome. They will solve any GC pose problems that you probably had in the past. They're super easy to tune. You just give them more heap and they will just work perfectly fine. They will give you very short poses, no problem on that. Which one to choose? Well, if you're stuck with JDK 8, you only have one option. You have to use Shenandoah. But if you use JDK11, you can choose between the two. It depends really on, you gotta try both. I personally think that ZGC is perhaps simpler in a way. Shenandoah is more sophisticated. It copes with many failure cases in a better way. But again, those failure cases should never happen. You should, do and size your heap properly, typically all of the time. But, if your load has a spike, then Shenandoah may cope with this particular load in a slightly better way. And then if you do use them, report your feedback, because it's important for them to know that you're using and that, your poses went really well. So just to give you like a couple of numbers of my testing, which is my particular own testing for my particular own application, I've run one of the benchmarks that we have for Jetty and another project called CometD. And G1, so this load that I imposed on this load benchmark was something like 5 gigabytes per second allocation rate, which is a lot. Typically, it's quite a lot. And I was having poses with G1 around 30 milliseconds. And this is a use case where most of the allocation was actually dying really soon. And so it was a use case that was very good for G1 as well. And it was giving, 30 milliseconds. ZGC went down to 2 milliseconds and Shenandoah as well. So, that seems like in absolute value, not much of a big deal, but these collectors are awesome, especially if you have long poses. They are so much better than anything that was previously available in hotspots. So I recommend you try them out and give it a go. Thank you for listening.